Welcome to Spelling Bee Ninja, where we explore the fascinating world of education. Today, we're diving into a topic that combines adventure and knowledge: the mathematics behind space exploration. Join us as we discover how math has propelled humanity into the cosmos, guiding every rocket launch and satellite orbit. If you're passionate about learning, don't forget to subscribe for free educational content that inspires and ignites curiosity. Mathematics is often referred to as the language of space exploration. This title stems from its essential role in enabling human beings to leave Earth's atmosphere and embark on extraordinary journeys into the cosmos. From the precise calculations needed for launching a rocket to the complexities of orbital mechanics, mathematics is crucial. Every space mission relies on rigorous mathematical computations to determine launch windows, calculate fuel requirements, and predict spacecraft trajectories. For instance, NASA employs over 1,000 mathematicians, using more than 100,000 calculations per second to ensure spacecraft stay on course and gather data accurately. This illustrates just how vital mathematics is to space exploration. It's not merely a subject, it's the backbone of our endeavors beyond Earth. One of the foundational aspects of space exploration is orbital mechanics, which utilizes advanced math to understand how spacecraft move in space. This field is grounded in Isaac Newton's laws of motion and universal gravitation. To put it simply, the orbit of a spacecraft is influenced dramatically by its speed and the gravitational pull of the celestial body it is orbiting. The paths taken by satellites and spacecraft are often elliptical, not circular, and mathematicians use precise equations to chart these orbits. For example, a spacecraft aiming to achieve Earth orbit must reach an astounding velocity of approximately 28,000 km per hour. This speed allows the craft to balance gravitational pull and inertia, successfully entering a stable orbit. Interestingly, the International Space Station orbits our planet at about 27,600 km per hour, completing an entire orbit roughly every 90 minutes. Maintaining that orbit requires continuous calculations to ensure it remains at the correct altitude. The math behind rocket launches is equally critical. Engineers engage in meticulous calculations to formulate the optimal flight path, the required thrust to overcome Earth's gravity, and the exact amount of fuel necessary for the mission. These calculations are rooted in fundamental principles like Newton's second law, represented by the formula F equals ma, meaning force equals mass times acceleration. Essential to these calculations is the Tsiolkovsky rocket equation, a groundbreaking formula developed in 1903 that remains central to rocket science today. It explains how different masses and exhaust velocities influence a rocket's ability to change speed in space. Fun fact: every pound of payload typically needs about 10 to 20 pounds of fuel to achieve orbit, an astonishing ratio. Next, we consider how spacecraft navigate through the vastness of space, a process that relies on intricate mathematics. Navigation involves an array of methods, including star trackers, which match observed stars to a database to determine position, and inertial navigation systems that utilize accelerometers and gyroscopes. Multilateration is another key mathematical technique, using distance measurements from multiple points to calculate a spacecraft's location. As spacecraft journey deeper into space, they must account for relativistic effects, the differences in time as expressed in Einstein's theory of relativity. For example, communication with the Voyager spacecraft, which has traveled over 22 billion kilometers from Earth, requires precise timelines since radio signals take hours to reach it. Speaking of communication, mathematics serves as the backbone of how we relay signals between our planet and spacecraft. Signals traverse space at the speed of light, around 300,000 kilometers per second, necessitating exact timing for transmission and reception. Mathematical concepts help ensure data integrity during transmission, including error correction codes, signal processing techniques, and considerations for Doppler effects that arise from relative motion. The power of these signals diminishes with distance according to the inverse square law, meaning that as distance doubles, the signal strength drops to 1/4. Consequently, careful calculations are vital to maintain contact with exploring spacecraft, particularly those on distant missions, such as rovers on Mars, where signal delays can span 5 to 20 minutes depending on Mars's position. Power management also relies heavily on mathematical calculations. Engineers must ensure spacecraft have sufficient energy to operate effectively. They do this by calculating power needs using the formula for energy, which is voltage times current times time. Additionally, as missions begin to venture beyond Mars, reliance on solar energy diminishes. Thus, calculations must determine the viability of nuclear power as a reliable energy source. Each instrument on a spacecraft consumes power, and determining how to generate and store sufficient energy for these instruments is critical to mission success. One fascinating insight is that the Parker Solar Probe, even when situated very close to the Sun, requires continuous power calculations but produces enough energy to power a large home. As we look at deep space missions like Voyager, we encounter unique mathematical challenges due to the enormous distances involved. This mission has faced obstacles such as computing trajectory adjustments using gravity assists from planets, accommodating decreasing power outputs over time, and predicting communication delays that can span hours. Despite its launch over 45 years ago, Voyager continues to relay valuable data, thanks to the robust mathematics embedded in its programming. Remarkably, the Voyager Golden Records, sent into space, contain mathematical illustrations to communicate our solar system's location to any potential discoverers we've yet to meet. Another exciting challenge involves the precision required for landings on Mars. Due to the Martian atmosphere, which is much thinner than Earth's, parachutes are far less effective. Mathematicians calculate the spacecraft's entry angle and the exact timing for parachute deployment, while also planning for thruster operation. The landing sequence, famously dubbed the 7 minutes of terror, encapsulates the tension and excitement during this critical phase, where hundreds of thousands of calculations run automatically to ensure a successful descent. If timing for the landing event goes awry, even by a fraction of a second, the consequences could be disastrous. The most recent rovers like Perseverance are guided by years of mathematical advancements drawn from decades of Mars exploration. Lastly, consider the role of mathematics in the functioning of space telescopes like Hubble and the James Webb Space Telescope. These sophisticated instruments depend on precise mathematics not only for their operational orbits but also for directing their observations. Algorithms process vast amounts of data captured from distant cosmic events, while optics mathematics helps in reconstructing images from raw data. The James Webb Telescope, with its 18 segmented mirrors, requires alignment with nanometer precision. Fun fact: the Hubble telescope uses mathematics to negate the blurring effects of Earth's atmosphere, producing images significantly sharper than those of ground-based telescopes. As we look toward the future of space exploration, a landscape of new mathematical challenges unfolds. Human missions to Mars will usher in complex problems involving life support systems, radiation exposure, and psychological considerations for crew members. Planned interstellar missions introduce the need for new mathematical approaches for navigation and communication over interstellar distances. Sphere of influence calculations, trajectory optimizations for extended missions, and even quantum computing will come into play as our pursuit of knowledge extends farther into the universe. In summary, the mathematics of space exploration is not only about numbers and equations, it's a thrilling synthesis of human ingenuity and curiosity. From the launch of rockets to the intricate calculations that keep us in the cosmos, math shapes our understanding of the universe and helps us turn dreams into reality. So, stay curious, keep exploring, and who knows where the next numerical equation might take us. Today, we explored the vital role of mathematics in space exploration. From launching rockets to navigating deep space, every mission relies heavily on precise calculations. We discussed how Isaac Newton's laws inform orbital mechanics, and how rocket launches depend on careful mathematics to ensure success. We examined the challenges of communication and power management for spacecraft, along with the calculations that are essential for landing on Mars. Finally, we glanced into the exciting future of space exploration where new mathematical challenges await. Remember, the cosmos is an intricate tapestry woven with the threads of math, science, and human ambition. Thank you for joining us on this enlightening journey into the math behind space exploration. We hope you found it as captivating as we did. If you're eager to learn more, subscribe to Spelling Bee Ninja for more exciting educational content. Until next time, keep dreaming, keep learning, and keep reaching for the stars.